And I'm also projecting. So I hope you in the back can hear me. And you aren't going down because I'm loud. So, my talk, refactoring InfluxDB from gogo. First, I wanted just to give you a little bit about me so you know who I am, where I'm coming from. In a previous life, I was a Ruby developer. I wrote this book, Service-Oriented Design with Ruby and Rails. I organized the, this is going to be really difficult. I have 94 slides to get through. Woo. I organized the New York City Machine Learning Meetup. It has a lot of people that come to it.
Just have to anticipate your slide changes.
Is it really this slow? Oh my god. I'm the series editor for a book and video series for Addison Wesley called Data Analytics. And I'm obviously the co-founder and CEO of InfluxDB. All right. On to the talk. But first, I have a confession to make. This is actually not a Go talk. This is a talk really about API design and software design and how this principle, optimizing for developer happiness, which is one of our key goals in InfluxDB, ultimately motivated us to do a huge refactor of the code base. And actually, all right, is there a hookup for this? This is no way this is going to work. It motivated us to do a refactor, which was actually, it was so big it turned out to be really a rewrite of InfluxDB. Let me just really quick talk about what InfluxDB is. It is an open source distributed time series database written in Go with no external dependencies. That means once you install it, there's a single binary, and the whole thing just works. You don't have to install Zookeeper, you don't have to run Redis or Cassandra or whatever. It's useful for metrics, for time series data, obviously, time series database. It's useful for analytics. And it's also useful for events. So this is like a Apache log file. If you look at this, like when I look at this, I see discrete events, but I also see hundreds or thousands of discrete time series here, right? 200 responses over time. Hits to a specific URL over time, that kind of stuff. The use cases we're designing it for are metrics. And when people think about metrics, most of the time that's DevOps data, right? There's sensor data, and also there's real-time analytics. So I think going over some of the features will help illustrate why it might be useful to you. So first, let me talk about the data model that it uses. It's a bit different than a SQL database or any of the other NoSQL databases that exist. Well, first, you do have an idea of a database, like an SQL. And then you have these things called measurements. In SQL land, you probably think of these things as like tables. In our case, measurements map to something that you're measuring, like CPU load, temperature from a sensor, log lines that you're taking, clicks. So some of these things are discrete events. Some of them are samples that you take at regular intervals. Then you have tags. Tags describe the data that you're taking in. It's metadata that describe it, right? So tags are key value pairs. Say region equals US West, host equals server A, building equals 23, service equals Redis. Those are all tags. They're metadata that describe the measurements that you're taking. Then there's a concept of a series. A series in InfluxDB is the combination of a measurement and a tag set. Now, series can actually map to real underlying series in the database, or series can be composed on the fly based on a bunch of other series that you merge together. So one series would be, say, CPU load and region equals US West. That's a series. Now, under the covers, that probably maps to hundreds or thousands of series that you're looking at. Then within the series, within a specific series, you have data points. Data points have fields which can store different kinds of values. booleans, integers, float64, strings, or bytes. So unlike a pure regular time series database like Graphite or OpenTSDB, in those you essentially have your series and you have a single value, which is a float64. With Influx, you can have multiple values associated with each individual data point. And then finally, you have a timestamp, which is a nanosecond epoch. All right, so writing data. There's an HTTP API. It's pretty simple. You do a post to this thing. The post that you do looks kind of like this. You have an object. You specify a database. You specify a retention policy that you're writing into. In our case, 30D means we create a retention policy where we keep the data around for 30 days. And then you have the data points. This is an expanded, very verbose way to write in the data. But there you can see you have a measurement name, you have the tags that describe the point, you have a timestamp, and then you have the fields. Querying is also very simple. You do a get on this URL, and you pass it a query string. In our case, we designed a query language that looks kind of like SQL. It's not true SQL. We bastardized it to make it good for our use case. So this is what some of it looks like. I'm not going to go through every single example. I'm just going to show a couple of highlights. Here we're saying select value from CPU where host equals server A. So host equals server A, in this case, is a tag. Value is a field. The results that we get back, we see we have the query here, we have series, and then within this we have series is a collection, right? So in our case, we're just looking at one series, which is CPU host equals server A. Here we have the columns, time, and value, and then you have the collection of values. And they're ordered by time. Here's one where we say, okay, give me the value from CPU where host is either server A or server B. So in this case, we get two separate series back. One that's host server A, one that's host server B. Here we're taking a percentile on the fly, 90th percentile CPU for the last 4 hours in 10-minute increments grouped by the region. So we're saying, for each region that we have, give me the 90th percentile in 10-minute buckets for 4 hours. So we get, in our case, we only have servers in US West and US East. So we get two series back, and we get those values. You can take multiple aggregates in a single query, mean, percentile, min, max, multiple different percentile levels. And there you can see you can group by different time intervals. You can group by seconds, minutes, hours, days. Here, we're doing a query to return all the unique series within CPU. So we're saying, get the mean value in 1 hour increments, 1 hour buckets for the last 48 hours, group by, and this is like a special thing, group by star. So that just tells it, expand this out into every single series that we have. Now, depending on how many of these you have, you may not want to do this query. You may end in sadness because you're going to get back an insane amount of data, but it's something you can do. One of the other things in the new release that we focused on was being able to do discovery of data based on tag values, right? The whole idea of tags is metadata that describes these measurements, and that aids you in discovering, okay, what measurements are we taking? What are the different values we have? Like what services are we running? What hosts do we have? That kind of stuff. So some quick examples here. The query is show measurements. The result, we just see, oh, we get the names back, right? So we have CPU, memory, network, whatever. Here we have show series. So again, a series is measurement plus tag set. So for each measurement we have in the database, here we're just showing one, CPU. We'll show the columns, ID is always going to be there. Each series has a unique ID. Then region and host are tags that describe data that is in CPU. So we can see, okay, we have US West server A, US East server B. Here, we're saying, show me all the measurements where the service equals res. So we're saying, okay, what measurements are we taking for our res services? metrics, yes.
Did you just have a JSON document with the same key twice?
Where? Oh yeah, that is a typo on my slide. Okay, thank you. Ignore the double name thing. So yes, there you see like what the measurements are. With tags, obviously they're key value pairs. So here we're saying, show me the tag keys from CPU. So we can see what are the different tag keys we have to describe the CPU measurements, region and host in that case. Or we could say, show me the tag values for the key equals service. So this shows us what measurements we're taking, what services are reporting data. So here we can see, oh, we have Redis and Apache are both reporting data. And there's a lot more underneath there's a lot more in terms of features and things that it does. I didn't want to make this exhaustive because I wanted to get to the rewrite stuff. There are retention policies, there's automatic downsampling and aggregation, there's clustering, and some other things. All right, let's talk about the rewrite. Since November of just last year, we've been basically rewriting InfluxDB from scratch. Now, most people, when they think about a rewrite, they think of this article from 2000 that Joel Spolsky wrote. And in it, he says, on the topic of rewriting software from scratch, it is the single worst strategic mistake that any software company can make. He was talking about Netscape rewriting their whole browser. So we know this. I know this. I read that article I read it back in 2000. I probably read it like 3 times since then, and talked to a bunch of people smarter than me that all agree rewrites are totally insane. So if smart people are saying this, why in the hell would we do it? This. I mentioned this before. Optimize for developer happiness. This is one of the things we want to do. Now, this is kind of like a touchy-feely thing, right? Like optimize for developer happiness. What the hell does that mean? In our case, I think about it from 2 different perspectives. We have the InfluxDB users, right? So what does it mean for them? It means simple setup. It means a flexible API that lets them do a range of things. It means an empowering API. What do I mean by an empowering API? I think of an API that empowers them to write less code and get more done faster. They can do things that they previously couldn't do because InfluxDB didn't exist. And it should be performant by default. When they use the API in the default way that they're using it, it should just give them good performance out of the box. They shouldn't have to do a bunch of things and jump through hoops to get the performance they want out of this piece of software. Ultimately, it's something that helps developers build analytics applications faster. That's the thing that we're focused on, right? Analytics for DevOps, analytics for sensors, analytics for business intelligence or user analytics, whatever it is. So the other side of it is InfluxDB developers. Now, right now, that's me and the other people who work for InfluxDB, and probably about 45 people who have contributed around the world to the code base. But hopefully that number is going to get bigger. And for them, and really this is for Go programmers, right? Because it is a project written in Go, we want a fast build time. We want idiomatic Go code. When we started InfluxDB, the 3 of us who were writing it initially wrote a lot of Go code that is not idiomatic. I'm probably more guilty than Todd and John were writing non-idiomatic Go code. I'm learning. So we wanted that, and we wanted to be easy for people to build the project and contribute to it. And if it's going to be easy for them to contribute to it, idiomatic Go code is going to help them. But also, the organization of what is where helps. It needs to have clear entry points so that people can say, oh, I want to write this new aggregate function, so this is where I can go in the code, and it's pretty simple to do. And then this was the other one. This is just a snapshot of GitHub. It shows 290 open issues. I've had people heckle me before about the number of open issues on the project. I think it's a double-edged sword. It means people are paying attention. Anyway, looking at those, like, we want to figure out how to resolve all those as quickly as possible. And looking at all those issues, they're split across what I call 3 different legitimate areas of concern. The first is feature requests. These happen all the time, right? People want moving average, they want different kinds of derivatives, they want ways to fill in data in different ways, top, end for a given period of time, exact data point for min-max. There are tons of features that people are constantly coming to us about. There are performance bugs. So things like, there's a high CPU load on the query. Like I do a query, it pegs the CPU, but actually it only pegs one CPU, and Go's supposed to be able to use every processor, so why the hell is it only pegging one? And, oh, if I do a query and I say where food equals bar, it takes too long. Or if I'm listing different series in my database, it takes too long. And then there are just straight up bugs that are in the source code, right? The number of open file handles goes over what they've set, and the database doesn't shut down gracefully. It just kind of dies. Or we run out of memory and the database dies. The clustering stuff doesn't work. So then the last one, so those were the 3 legitimate areas. This is the other one. For any of you who run open source projects or contribute heavily to open source projects, I'm sure you love this when people like come into your GitHub issues and they ask a question. Now, for the most part, I would say those are legitimate. However, they do give us some important information. Some questions that people ask point to bad API design. They point to things and improvements that we can make. They'll make the software easier to use and easier to understand. So I don't think they're all illegitimate. So based on that, we identified 3 different areas of improvement. These: API design, structural design problems that were limiting performance, and underlying technology choices that were causing bugs that we couldn't chase down. So we'll take each one of these in turn. Now, API design. Goals: it should be understandable. It should push users in the right direction. When they use the API as they naturally feel they should use it, they should get expected results and they should get expected performance. So our previous API, we were pushing people to have many, many different time series and have them encode the metadata of the time series in the name. So this is very similar to how you do things in Graphic, right? You have all this metadata, you have these long time series names, and there's a huge list of them. So another thing about understandable API design was this feature we had. Well, the feature now is called retention policies, which is the idea of in a time series database you have data, high precision data that you keep around for a short amount of time. You aggregate and downsample from that and keep medium precision data for a longer period of time. And then you have lower precision data that you keep even longer. Influx manages all of this for you automatically, and that's a goal. Previously, this feature was called shard spaces. How users configured it was they would create a shard space and they would tell the database, for any time series that matches this regex, put it into this shard space. So that's where these series names come in, right? They say, oh, if it matches this, like this, then put it into the high precision stuff. If it starts with 5M, put it into the medium precision stuff. And all of this kind of counted on the user configuring things in a certain way and getting it just right. And the problem was it was really too hard to use, and a lot of people couldn't tell where their data was going. And even worse, if a user added something later, if they added a new shard space later and added in a different regex, it was possible for them to hide data that was previously available, which is the absolute worst thing that can happen, right? So our solution here was to have the user be explicit at write or query time. Again, this is just an API design choice, which was, do we have this regex method where it's all kind of implicit and they can't really control it, or do we have them just be explicit? explicit turns out to be the easier choice for usability. So an example of pushing users in the right direction is tags. So users wanted to do a query like this. Select a mean value from CPU where host equals server A. When they were writing in data, that's what they want, right? And previously, host equals server A was a column. So host was a column, and then we have all these strings. We didn't do anything with the strings except for just write them into the database. So they ended up being a bunch of wasted space. So then we thought, okay, well maybe we can add indexes. We can add column indexes that allow people to index their data. The problem with that is that the user still has to create those indexes. If everyone is expecting strings to behave like tags, we should just do it that way. We should just index that data and have it so that people can query on it and have it be fast and efficient. Don't make them create indexes when we already know what they want. Okay, structural design problems. So like I said, we told users to have many, many different series. And how they would pull these out is they'd say, oh, list series where it matches this regex. Or if they're merging a bunch together, they would say, select a mean value from merge. Here, this is the example of getting the mean of the US West region in 5-minute buckets. Now the problem with that was there was no way to make this perform well if they had greater than 100,000 series. And in this use case, it's actually trivial for people to have hundreds of thousands or millions of separate time series. And if we're matching against regex, you just have to loop through all of those and find the matches. And there's no way that was actually going to scale and be performant. So our solution is to use tags, and the combination of measurement names and tags break up the namespace so that it's manageable. So you're never iterating over the entire namespace of a million series to get back a result. So another example of a structural design problem is the query engine. So in the previous version of Influx, the query engine would pipe all the raw data over the network. We'd run the computation and send the summary text back to the user. Now, one of the whole reasons we wanted to write the database from scratch is we wanted to design a query engine where people would get data locality, right? That's the thing that we learned from MapReduce. You ship the code to where the data lives, not the other way around. So the solution there was to completely refactor, or essentially rewrite the query engine so that it followed a MapReduce paradigm. All right, last bit. Underlying technology choices. So here are just some of the choices that we made that were having an impact on us for performance or usability or whatever. So we're using protobufs to serialize the data. This is both over the network for intra-cluster communication and also in the database itself, in the underlying storage engine. This was causing a problem with performance. Basically, any query that would iterate over, say, a couple 100,000 data points would have to marshal them all using protobufs and then do something. So that's the point at which you'd see your CPU get pegged. And the thing about the protobuf stuff is use of protobufs was everywhere in the code. It was throughout the code base. So our solution was to switch to raw bytes for storage so that we actually don't have to marshal data. We don't have to serialize and unserialize it. We just use raw bytes. Another technology choice we made early on was to use LevelDB as the storage engine. There were two really big deal breakers for us with LevelDB. The first was it opens too many file handles. Under the covers, we actually have many databases open to represent different contiguous blocks of time. And that we do that so that we can evict data efficiently when it comes time to evict it. So there's really no way to hack around it. We need to have multiple databases going. LevelDB on a large database will have tens of thousands or potentially 100,000 open file handles. If you have 100 of those in a single process, you exhaust your file handles even on a modern system. And the other one was LevelDB doesn't support online backups. To do a backup, you actually have to close the database, copy all the files, and then read it. And those things made it really, really hard to transfer a shard from one server to another. So our solution was to switch to Bolt DB. I think doing a full discussion of Bolt is probably outside my time range. But if people want to talk to me about how we use Bolt and how we hack around write limitations and all that other stuff, catch me afterwards. Another one was we used flecks and bison for the parser. These were very hard to understand and update. There are some people who love to write Yak grammars, but I'm not one of those people. And it also has gogo, which was kind of sucky from a build perspective. So our solution there was to switch to a pure Go parser, which is easier to understand, easier for people to come in and actually add to and modify, and we don't have to deal with gogo. So all of these things together point to a rewrite, right? We have large API changes, we have underlying technology changes, and we have code in every area getting touched, right? If we're removing protobufs, we're pretty much touching all of the code across the base. And if we're changing the idiomatic Go code, we're pretty much touching every file in the project, right? My contention is that a refactor would have been a rewrite just dragged out over time, right? And some of these things were actually making underlying breaking changes, which means people upgrading to new versions would have to perform painful migrations to get it done. So a refactor over time would stretch these breaking changes out over a longer period of time. If we just rewrite it all in one go, we can rip the Band-Aid off quickly. We have one migration that people can do to get from 08 to 09. And ultimately, we felt that the rewrite path was the path that would best help us serve this goal, optimizing for developer happiness. And 090 gives us a solid foundation to build on and actually drive forward to 1.0. So, that's it. Oh yeah, we have shirts in the back. They're free. This is what the shirt looks like. Do I have time for questions at all?
Yeah.
Are you guys do you have any tools where people have data in MongoDB, for example, which is like time series data that they can import into the level DB?
What's that?
Are there any tools with InfluxDB so that someone can import the MongoDB data into Influx and from there
tools to convert data from another database into InfluxDB. There are people just written one-off scripts. We haven't written anything specific. The problem is there's so many different ways to structure your database and whatever your data and whatever database you're coming from. It's kind of like you have to write a script for it. Yeah.
So two-part question. First is, when is 090 coming out? It just gets a guess. And the second is, are you guys addressing anything with clustering?
Yes. So the work on 090 actually originally started as a rewrite of clustering. And it was just going to be the clustering piece, and everything else was going to remain the same. And then we decided there was going to have to be a bunch of other stuff. So sometime in March is the target for 090. We should have early testing builds out at the end of this week. Maybe not until Monday, but they'll be there so you can actually test out the API and try things out. And then over the course of the next 4 to 6 weeks, we're going to be doing filling in a couple of gaps on the features and doing performance testing and debugging and all that other stuff. Clustering, yes, totally rewritten. I'll have to talk to you afterwards about the design of it and stuff. All right, perfect. In the back?
How long did the rewrite take you?
The clustering work started in late August, but it was just Ben working on it. And we didn't really start the full work on rewriting until mid-November. So from a project perspective, the rewrite has actually been quite painful. It's painful for me as a creator and one of the owners of this project to see people asking questions on the mailing list and logging bugs and knowing that like we want to fix those things, but the problem is like we just need to get through this rewrite. So essentially, it killed our velocity on any feature development or bug fixes since mid-November. But my feeling at this point is after we get it out in March, we're going to be in a much better position, and then at that point, we'll be having incremental improvements along the way to fix bugs and add features. So it's basically like the pain of 4 months. Like we're not Netscape writing a multi-million line code base that took multiple years, right? We're like, I don't know, eight people at this point rewriting a code base that like 2.5 people wrote over like 8 months. So, yeah. Yeah.
So I've been looking at Flex for the past few months. It sounds like in a good spot to wait until you guys are done with it now. But is there like a migration path for it for people who are already using it?
There is a migration path from 08 to 09. We haven't built a migration tool yet. There is a web page on the current doc site. If you go to 08 and you go to schema design, it tells you exactly how you should structure your schema in 08 so that you can migrate it cleanly to the 09 structure. All right, I think I'm out of time. Thanks, everyone.